Hi, all. I hope you can hear me. Let me share my screen. Unfortunately, there was a power cut, so I was not able to log in. Yeah, so let me share this. I hope you can see me, right? I hope you can see my screen.
Yes.
Yes, okay. So unfortunately, because there was a power cut, I believe for today's session there will be two videos. So I'll upload both of them uh, because one part is already recorded and one part of that is saved already. So I'll upload that part as part one and then the second one as part two. Let's okay, continue. Let's try to continue what we were doing. So let's say what we are or what we were doing is that we have a straight line, and then let me just draw the distribution which looks, let's say, something like this. And then we have our mean, which is 29,000 rupees. This is my mu. And what I said is that there will be some point over here which I'm going to call the critical point. This point is also known as the Z critical point or the X bar critical point. So let's directly go ahead and try to calculate this, because as you have just seen, I'm interested more into this area so that I can reject the null hypothesis, right? And then I can try to prove my own hypothesis. Now, how do you calculate the value of Z? We have already seen the formula earlier. We know what is the formula for Z, right? We know that it is that random variable X. Then I have to take the mu, and then I need to divide it by the standard deviation, right? This is a very simple formula. We have already seen this earlier. But we are slightly going to tweak this formula over here because we are talking about a sampling distribution here, which we have already seen that sampling distribution, which is actually normal in nature, follows the central limit theorem. And in case of the central limit theorem, we have also discussed the standard deviation is also known as standard error. While standard error is basically standard deviation divided by root of n, where n is the number of samples, right? So I'm going to replace this standard deviation sigma sign with sigma divided by root n, where n is going to be my sample. So I need to know what is n, right? As part of my experiment, do I know what is n? Yes, the answer is yes. I've sampled 400 houses in West Bengal, right? So I know the value of n. The value of n is equal to 400, right? I know the value of standard deviation, which is 8,000. So it is 8,000, right? Then I have this x. I'm not going to write it as x anymore. I'm going to write it as x bar. Why? Because this is a sampling distribution, and that's why I'm going to write this as x bar, which I'm going to take as the value that I'm actually looking for, right? And then I have this value, which is my mean, right? So I have all the values. I have all the values in place, and then I should be able to do my z calculation from here, right? So it is quite clear that I have all the values with me, where I have this x bar, which is, let's say, it should be the 30,000 value. No, no, sorry, I did a mistake. I believe this mean is 29k. No, this is not a 29k. This is 30k, right? I think I made a mistake in my question, or in the sampling that my product manager had calculated. The mean was actually 30k. The standard deviation was 8. So this becomes 30, right? And my finding is going to become, or the one that I'm trying to find is 29, right? But what we usually do is that because we are interested in finding this, we consider this as the mean. So what I mean by that is this, sorry, the distribution that we have over here, we assume that this distribution belongs to a situation where we already have satisfied our a hypothesis which we created of that of 29k. So that's the reason why we are simply going to swap this value, right? So we are going to say that my random variable x bar is now going to be 30,000 and my mean is going to be 29,000. Why is this the case? Is because this sampling distribution will be assumed to be that of the hypothesis that I am trying to test. Now, if I put all these values, the values that I have got over here, so 30 comes over here, 29 comes over here, and so on. If I put all these values and try to calculate this, as far as I know, this will come approximately equal to 2.5. So if I take just a pen, let me just write it over down. So if you do a calculation from your side, you will come to know that this comes almost equal to 2.5. It will not be exact. This is just round to 1 point after the decimal. Why we are doing round to 1 point after the decimal is also going to be interesting, because if I take more values after the decimal, it's going to confuse me later on. Having a single value is going to help me, because now I'm going to use that concept of confidence interval. Okay, so the interval until where I have a confidence from left to right, let's say until this point in time, I have some confidence, or I need to have some confidence on the the status quo. Anything beyond this is the critical area which I'm actually looking for. Right, so that's why it is called the confidence interval. Now, since 2.5, the computed value of 2.5, right? So is 2.5 is the computed value of x. This falls over here. So this is the value here. Now, if this falls into this area, right? If this falls into this area, right? Then I can clearly say that I can reject the null hypothesis and introduce the product line into the new area. Now, how do I know that 2.5 falls in this area or 2.5 falls into this area? If you remember our calculation of that alpha and beta, or the type 1 and the type 2 errors which we had calculated, type 1 error is where the reality is that I have rejected. Okay, I have to reject, or it's a false case of the COVID-19 patient, or a patient actually does not have any COVID-19 disease at all. But basis my testing, I have found it to be true. So that's called the type 1 error. I also represent this critical point as the point where or beyond which I am supposed to make the type 1 error. Right? Now, why I say this is that I can define a boundary until which I have successful inference, and then anything over on top of this point, this is the kind of question that I'm asking. Maybe this is a one tail test, but that is why the impact may be less. But this is the kind of question that I'm asking. This limit is going to decide how much correct or how much wrong I am. Right. So that's the reason why this is point, or this line of this x bar c, or the critical line. It's also sometimes referred with the same notation of the type 1 error, otherwise known as alpha. And usually, and this is a general practice, that if I would like to accept or reject any hypothesis, my confidence interval must be 95%. Why? Because in the central limit theorem, while I applied the x, I'm sorry, I'm actually forgetting the name, x, yeah. So when we applied the empirical rule, if we looked into this formula, right? So this is mean plus minus standard deviation, or mean plus minus 1 standard deviation. This is mean plus minus 2 standard deviations. Anything beyond that is very, very rare, right? Because it is very, very rare. Okay. Now, in totality, we can have only a guarantee or a setup with only 100% kind of a validation, right? So if I have already covered 95%, then what is left out? The left out value is only 5. So I have total 100. If I have already covered, let's say 95, and 95 is my confidence interval here. So usually this is the industry standard that we are going to take. The confidence interval being equal to 95, so that I can cover mean plus minus 2 standard deviations. This much of range I'm trying to cover. Then, if it is anything beyond this, or on this side as well, on any of the sides, then I can simply reject the null hypothesis. Now, how do I do that? If this is 95, so let's say if this portion is what covers 95, and this entire graph is that of 100, then it is very clear this part is 2.5 and this part is 2.5, right? Because then only 2.5 plus 95 plus 2.5 is going to make the 100% a sampling distribution or the range or the area under the curve, right? This is one way of looking into it. It helps to understand the context. It's not the exact or a detailed mathematical way, but it is a quite a good visual way that if this is 95% and I have only 5% of space left, then this is 2.5 and this is 2.5. If this is 2.5 and my z value is falling directly on this line or anything beyond this point, this is my interest area. So then I can simply reject the null hypothesis. I can reject the null hypothesis because my value of z falls on this critical line, which I've also denoted as x bar c, which I've also denoted as zc, or which I have called the area beyond the confidence interval, or the area beyond which or beneath which I can have type 1 kind of errors, is where my point falls. So it is inclusive of this line as well as beyond it. So if it falls anywhere in this area, I can clearly reject the null hypothesis. So let's try and see what was my null hypothesis. Null hypothesis mu should be less than 29,000, right? And alternate hypothesis is this, right? So basically what my product manager was saying, she was right actually. She was saying that I needed to have an average monthly income greater than 29,000, somewhat less standard deviation. That's right actually. Then we should make a launch. And we should make a launch in this case also. Why in this case is because in West Bengal, I've already seen, irrespective of how much is the standard deviation, I have a mean household income which is greater than or equal to 29,000, right? And hence, I'm going to make a launch in this case. So that is the inference that I am making, right? Let's try to quickly recap what we have seen, because if we are going to look at this for the first time, we are going to have doubts. It is quite obvious. Please don't worry. If you have any questions, let's look into this one more time and then we can ask the question. Sorry, what am I doing? I'll have to take a curvature, right? So let's say this is the standard deviation, right? Oh, unfortunately, the current has come back. Maybe the internet is going to disconnect once more. Okay, let's see if it is going to disconnect. Fine. So this is my mean value. In this case, what I am considering as the mean value, the value that I have considered as part of my hypothesis test. So I'm going to consider mean as 29,000, 29K, okay? Not the sampling mean, okay? Not the mean of the sample that I'm going to consider, because this is a sampling distribution of what I'm expecting what is going to be. So that's why this mu will be denoted by 29K, okay? I need a critical area. Why I need a critical area is because anything until this point in time is otherwise known as my confidence interval. Confidence interval is where null hypothesis, this guy, this fellow is going to live. So null hypothesis lives in this area. Until 0 to 95, this is his area. This is his den. In his own den, you cannot kill the king of that den, right? So in this den, the confidence interval is where the null hypothesis lives. Okay, it is live, it is the king here. So that's why I need some kind of critical or x bar c or zc, also denoted as, which is beyond the critical area, or it is the critical area beyond the confidence interval, also denoted by the letter alpha, because alpha also denotes type 1 error, where I have this critical area. Why is this denoted by alpha? I hope you got that, because alpha is where I am actually getting something which is known as a, how can I say this? This is going to be, let's say, uh, false negative, right? False negative is what I can call alpha, right? So now that I have got alpha, so this ZC value or X bar C value is something which I'm going to calculate. I'm going to calculate using a formula, which is X bar minus mu divided by standard deviation divided by root under n. So this is one entity, right? I have got all this information from my question. I need to get all this information. Okay, if I don't have all this information, I'll have to approximate things, which I don't want to do. In this case, X bar is going to be 30K, mu is going to be 29K, standard deviation is going to be 8,000, root under n is going to be root under 400. Okay, so n is 400, so this is root under 400. So if I do this calculation, I come to know that it is 2.5. Now I say, what is this confidence interval? Statistically, or market standard says it should be mu plus minus 2 standard deviation, right? If it is mu plus minus 2 standard deviation and this sampling distribution follows CLT, then I already know, as part of, let's say, the empirical rule, mu plus minus 2 standard deviation is covering 95% of the data. So if this line covers 95% of the data, let's again take a line. So let's say this is the line. Okay, so this is minus. So this part is what? Minus 2SD. And this part is, let's say, this line is, let's say, plus 2SD. Okay, that is the reason why this line becomes the confidence interval line, right? So this critical point becomes the critical point because this is where the confidence interval of my experiment is going to stop. This is where the null hypothesis is no longer confident beyond this point. It is not going to live. It is going to die. Right now, simply put, nothing fancy and nothing much mathematical at all. If this part is 95, this part is 2.5, this part is 2.5. Now I simply look at the value of ZC. If 2.5 is less than or equal to the, sorry, it should be greater than or equal to, right? So this 2.5, if it is greater than or equal to this value, right? So ZC, if it is greater than or equal to 2.5, then I can say it falls within this range, right? And I can clearly reject the null hypothesis because I am in the critical zone, and that's why I can reject the null hypothesis. If ZC had it been 1.5, could I reject the null hypothesis? The answer is no, because 1.5 falls over here. Why does 1.5 fall over here? Because this graph follows the central limit theorem. It is a standard normal distribution where the mean is considered to be at a 0th point, and then things move from here or here in this direction and that direction, right? So any critical value which is going to be less is going to move in this direction. Any critical value on the negative side will be here. Any critical value on the positive side will be here. Any critical value negative side will be on the left side of this line, of this mu line, right? Of this mean line. Because the value of ZC is going to increase on this side, as I go on the right hand side, the value of ZC is going to increase. Then as good the value will be, then I will be able to decipher that, okay, I can reject the null hypothesis and accept my alternative hypothesis. Was my game, this was my aim here. I would like to launch this because alternate hypothesis says mean should be greater than or equal to 29,000. In this case of West Bengal, I see that it is actually equal to 30,000. Hence, I'm confident I'm going to launch my product. Let me clear this and let me ask you if you have any questions. Any questions? Any questions? I hope you can hear me, right?
Yes, yes. No questions from my
Okay,
side.
okay, okay. Okay, I think that concludes one example of hypothesis testing that we have seen. There are many more examples that we can take, but overall, I believe you get the idea what is happening over here. So we are taking some data, we are trying to find out the sampling distribution, and then we are trying to simply figure out how we are going to accept or reject the null hypothesis. Now, what we are going to look into is a concept which is known as the significance level. Give me 1 minute. I'll be on mute. I'm actually getting a call. I'll be back in a minute. Yeah. Okay, I'm back. So let's try to continue. So what we are going to uh, look into now is that when we looked into this values, right? In this case, we calculated the z value or the critical z value, and uh, uh, in this case, that critical z value is actually uh, a kind of a probabilistic thing. Why is because we are trying to do an inference. That's one way to look at it. But then if it is really basis the sample that we have calculated. So if we have a very large population from when we are calculating a sample and then we are trying to understand the setup, then that becomes a probabilistic view, because we are sampling n number of artifacts and then we are trying to figure out something. We don't have the exact output. We have not really launched that product in some market, and we are not trying to test it there, right? We are trying to approximate. So that's why it's a probabilistic game. So let me just draw once more, although we don't have much time, but we are going to see how much we can cover. So this is my distribution, and this, let's say, was the value of ZC, right? So if value of ZC was what? We found out it is equal to 2.5. It fell in the critical area, and that's the reason why we have rejected the null hypothesis. So computed Z becomes 2.5, right? There is another way in which we can look into this. Okay, because computed Z is 2.5, there is a way, and I'm not going to derive the formula right now because it is going to take some time for me to derive the formula. Uh, by means of that, we can say that this critical Z value actually leads to a probabilistic value. We are going to see tomorrow how this leads to a probabilistic value. But if I convert this critical Z value, this is a scale-less kind of value, right? Because Z has no scale. So if you look at the formula itself, x bar minus mu divided by standard deviation divided by root over n, it is actually removing all the scales, because the numerator and the denominator are of the same scale, which is going to get cancelled. Because this does not have any scale, we can try to apply some test or some kind of a mathematical representation, which is going to convert this into a probability. And that probability is otherwise known as a p-value. Okay, there's some way in which you can convert this critical ZC into a p-value, which will be very important for you, because if you only look at the critical Z value, you may or may not be able to decipher all of the hypothesis tests. Why I'm saying this is because the example we took is a very simple example. It was a one-tail test. We are also going to look into examples which are going to be two-tail tests, right? In which case it will become very difficult for us to visualize everything and try to figure out what is right or what is wrong, right? So that is the reason why we need to sometimes look into the absolute value, because we are already studying, let's say, probability, and we know that until 0 to 1, so this is the range of the values that we can have, right? Probability can either be 0 or 1. 0 being the lowest point, 1 is going to be the highest point, right? So if I convert this 2.5 into p-value, which we are going to see how we have done that, this comes out approximately equal to something like 0.0062. We are going to look into the calculation tomorrow, right? But if I convert this becomes 0.0062, right? Why is this p-value so important? Is because this p-value is also known as the significance level, right? This is also known as the significance level. What is the meaning of the significance level? This is the level at which the null hypothesis gets rejected. So if I convert this into a percentage, I can clearly say that in this case, in the context of the example that we have taken, is that 62 out of 10,000. You see how many zeros are here? After dot, there are 4 zeros, right? So if I want to convert this into a whole value of 62, then I have to multiply this by 10,000, right? So in odds are less than, I can clearly say if p-value is 0.0062, the odds are less than 62 out of 10,000, that the sample mean of income 30,000 rupees would have occurred entirely due to chance. right? Means when my product manager went to Calcutta, or when my product manager did a sample of all 400 people from the West Bengal state, right? And I know that the population mean is what, 29,000 rupees, right? Because my population as of now for me is the people who are actually my customers in the state of Maharashtra. So if I take an average of all the salaries of all the people who are my customers in the state of Maharashtra, that becomes my population as of current date. I have not expanded to West Bengal. So my population mean is 29,000, right? Which I know already from the data. And then I'm trying to launch my product into West Bengal, where my sample mean is actually 30,000, right? So what this 0.0062 means is that 62 out of 10,000 are the odds that the sample mean of income 30,000 would have occurred entirely due to chance. That means the effect of any confounding variables is very, 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 very less. Right? It is very less. There is a chance of 62 out of 10,000, which is really very less. Right? That is the reason why. What do we say is this point, because 95% is my confidence interval, and I am doing a test on one side, right? So level of significance is something that I'm going to define now. It is applicable for two-tailed test, in which case this side and this side will be considered. But overall, if my confidence interval is 95%, my significance level is known as 5%, because it is the rest 5% part where my critical ZC, if that falls, I'm going to safely reject the null hypothesis, and I'm going to claim that alternate hypothesis is something I agree with. Right? So if 5% is known as significance level, I can convert the significance level into a probability value or a p-value, which is as simple as 0.05, because it is just a probability, a percentage to probability representation, right? So this calculation has no mathematics. It is really simple. I've simply converted the percentage into probability. So in this case, my significance value or my ideal condition p-value is equal to 0.05%. Or p-value is actually not into the percentages. I'm sorry. This is just the absolute value within the range of 0 to 1, where my p-value comes to be 0.05. This is with respect to my significance level. Now, if my expect or my experimented p-value is going to be less than this, right? If my experimented p-value is going to be less than 0.05, I can safely say that I am rejecting the null hypothesis. This is one way of solving the problem. This is one way of doing a hypothesis test, is to use the p-value. Why? Is because p-value is something that you can relate to more easily than the critical Z value. So what we are instead going to use later on in many of the cases, rather than using Z critical value, and you will see tomorrow why this calculation of 0.006 is actually comparatively easier than ZC, because you can actually relate to this value quite well, right? You can relate to this value quite well as opposed to ZC, because ZC itself is a very coagulated kind of a concept, right? After understanding 2 to 3 times, then maybe we get a context of what ZC is actually meaning, because it has no scale. At least we know that if we are getting a probability value, then it falls in the range of 0 to 1. And looking at that value also, I can see some kind of chances, I can see some number of odds and so on. So I can derive something. From this ZC value, it is going to later on become very, very difficult, especially when we are going to have two tail tests. Right? We had only one tail test over here because the tail is over here. This is my critical area, which I'm interested in. Tomorrow, if I'm interested in something here and something here as well, it's going to become very difficult which ZC to consider, how to calculate, and so on and so forth, how to reconcile. Although there is a method, but that method is really going to be calculated, but it is really going to be complicated. So rather than using ZC, p-value is one more way. You can say significance level or usage of significance level computed as a probabilistic value, otherwise known as p-value, is one way to calculate or one way to perform hypothesis testing. And it is a very relatable case, right? So tomorrow we are going to see how p-value is actually calculated, and we are also going to take another example. Right? I think that's all from me right now. Let me clear the drawings. Let me stop the sharing. I'll be sharing the documentation with you. Let's see you tomorrow. If you have any questions, please do let me know. Yeah. Thanks all. Thank you.
Thank you.
Thank you.